Hello everyone. So this is the first lecture of the rotational mechanics, and this is the first topic also, the moment of inertia. And you can say the most important topic in this chapter because if you see the previous questions of IIT JAM, almost one to two questions coming from this topic, moment of inertia every year. So you can understand how scoring is the topic is, and in case of GIST and TIFR, this is also one of the most demanding topic. So basically, we'll start with the definition of moment of inertia, and what it says actually, moment of inertia of a body about a given axis is equal to the sum of the products of the masses of the consequent particles and square of their respective perpendicular distances from the axis of rotation. So what it says, if we have an axis of rotation, let's say I, and a mass of m1 with a perpendicular distance r1 from the axis of rotation, then you can say that the moment of inertia equals to the mass times square of the perpendicular distance, which is in this case m1 into r1 square. So this is actually what the moment of inertia is. In case of multiple particles, let's say a particle m1 in a particular perpendicular distance of r1 and a particle m2 in a perpendicular distance of r2, and let's say the moment of inertia about this axis is I2, then I2 equals to simply m1 r1 square plus m2 r2 square. This is as simple as this. And in case of rigid bodies, simply we take elements and we integrate over the whole body, and we use the di equals to integration of dm of x square, where x equals to from the perpendicular distance from the particle and the axis of rotation. So let's go next. Here we will see the moment of inertia of different rigid bodies. First of all, the rod about a center, that is I equals to ml square by 12. A rod about its end, that is I equals to ml square by 3. In case of ring, I equals to mr square. In case of disk, I equals to mr square by 2. Solid sphere, 2 by 5 mr square. In case of hollow sphere, I equals to 2 by 3 m square, and a triangular lamina, which is important, triangular lamina, that I equals to m h square by 6, where h equals to height of the triangular lamina. Next, here we can see the square lamina, where we're rotating the square lamina about its diagonal, and the moment of inertia in this case is m square by 12. In case of hollow cylinder, it resembles the value of the ring, and that is equals to I equals to mr square. And in case of solid cylinder, we can see it resembles the value of the disk, circular disk, and that is equals to mr square by 2. A solid cone equals to I equals to 3 by 10 mr square, hollow cone mr square by 2. And in this case of rectangular laminar, where the side length of the rectangle is A and B, and if we rotate the rectangle about its center in a perpendicular of the plane, then you can see the I equals to 1 by 12 into m a square plus b square. So Next, we will see some to steps to find moment of inertia of rigid bodies. Actually, we will follow the same steps in every case when we are gonna find the moment of inertia of any rigid bodies. And the step one, that is equals to finding element. Let's say we are asked to find the moment of inertia of a rod about its end. We have to first take the element. Let's say in case we take the element dx, a small element dx. So this is our first step. And second step 2, that is finding elementary mass. Let's say in this case, in this case, the mass of the rod is m and length of the rod is L. So dm equals to m by L dx, where m by L equals to mass per unit length, mass per unit length into the element. So by this way you can get the elementary mass, and this will help you to proceed further. And next, and the step 3 is to put the equation dr equals to dm into x square, where x equals to perpendicular distance from the particle to the axis of rotation. Axis of rotation. These are the 3 steps which we will follow almost in all the cases of finding moment of inertia of rigid bodies. So in the next part of the video, we will find the moment of inertia of some important rigid bodies which I have told earlier. And first, we will find the moment of inertia of a straight rod wire about its center. So we are given a rod of radius L, and we have to find the moment of inertia about its center. So as I have told earlier, the first step, that is to take the element. So this is the element dx which we have taken, and the mass of the rod is m, and length is equals to L. So the mass per unit length is equals to m by L. So the second step which you have said, to find the elementary mass, that is dm. dm equals to mass per unit length into dx, that is m by L into dx. And the third step, that is di equals to dm into x square, where x equals to the perpendicular distance from the element to the axis of rotation. So now put the values m by L dx into x square, which is equals to m by L x square dx. Now to find the moment of inertia, the total moments of inertia, we have to integrate. The di, and that is equals to m by L x square dx. And we have to integrate the Now we have to integrate the rod from L by 2 minus L by 2 to L by 2. First we will move to minus L by 2, then we have to go to plus L by 2. So minus L by 2 to plus L by 2. Proceed further. L by L is coming outside. X squared dx, which is m by L x cubed by 3 plus L by 2 minus L by 2. And after calculation, we will get m square by 12. And that is the value of moment of inertia of a rod about its center of mass. And by this way, next we will find the moment of inertia of a circular rod about an axis passing through its center. Well, in this case also the first step is to finding the find the element. We have taken element of dx, and all in case of ring you can see that all the elements which we will take is at the same distance of radius r from the axis of rotation. So we don't have to vary the distance, we just have to vary this element, right? So in this case also, mass equals to m, and mass per unit length is equals to m by the total length. Total length is a perimeter 2 pi r. So the next steps to find elementary mass d, that is equals to mass per unit mass per unit length, that is m by 2 pi r into dx. And the third step is putting the value of di. Di equals to dm into r square. We put r square because the distance is not varying, this is constant. Okay, so that is equals to m by 2 pi r dx into r square. Now to find the total value of the moment of inertia, we have to integrate di equals to m by 2 pi r square dx. Now to put the value of the limits, we can see that we are varying the element. So we will vary. Let's start from this point. Let's start from this point. We will go around and then come here. So how much length we are following? That is 2 pi r. That is the perimeter of the ring. So the limit will be 0 to 2 pi. 0 to 2 pi r. That is equals to m r square by 2 pi r x 2 pi r 0. So proceeding further, m r by 2 pi r minus 0. So 2 pi cuts out. So that is equals to m r square. And that is equals to the moment of inertia of a ring about its center. Next, that is moment, we have to find the moment of inertia of a disk about its center. In the previous question, we have find the moment of inertia of a ring, and in this case, we have to find the moment of inertia of a disk. This question is the most important because if you find the previous question, then almost in 30 to 40% cases, the question is to find the moment of inertia of a disk. So let's proceed in the same way. The first step, that is to finding the element. So in this case we are taking the element, and that is the element of a ring. and we will integrate the ring from the distance 0 to r. Okay, so in this case also, mass equals to m, total area equals to pi r square, and the mass per unit area equals to m by pi r square. And the second step, that is finding the elementary mass, that is equals to Tm, which is equals to mass per unit area into the area of the element, that is 2 pi x dx. So 2 pi x is basically the perimeter of the element, the ring element, and dx is the thickness. So the perimeter into the thickness equals to the area of the element, the ring element which we have taken. So next, that is di equals to dm x square, where x is the perpendicular distance. Now put the value of dm, m by pi r square into 2 pi x dx into x square, which is equals to 2m by pi r square. Pi cuts out, and x is cube dx. So let's find the total moment of inertia, that is integral of di equals to integration of 2m by r square x is cube dx, taking out the constant terms, x cube dx. And in this case we will integrate the element from 0 to r, 0 to r, and that is equals to 2m by r square, r to the power 4, sorry, x to the power 4 by 4, that is 0 to r. So by calculating this, we will get I equals to half mr square, and that is the value of the moment of inertia of a disk about its center. So now we will find the moment of inertia of a triangular lamina about its base. So basically in this question we are asked to find the moment of inertia. We are asked to find the moment of inertia of the triangular lamina with this axis, of rotation. And here in this case also, the first step, which is to finding the element, we have taken an element, strip element, along the direction of y, and basically we will integrate this element from 0 to h along this axis of rotation. So let's proceed further. So in this case also, the mass per unit area is equals to m by half into bh, where b is the base of the triangular lemma and h is the height of the lemma. So here we get 2m by bh. Now the second step, that is to find the elementary mass of the element, of the strip element, that is equals to sigma into dA, where dA is the elementary area of the strip. But to find the elementary area, we need to find the length of dE. So to find the length of dE, we have some tricks. So to find the length of dE, we will use the Properties of similar triangles. Similar triangles. So from similar triangles, triangle ADE and triangle ABC. So this is ADE and triangle AB and C. So these are the two similar triangles, and from similarity conditions we can get that DE by BC equals to H minus Y by H, where H minus Y equals to the height of the smaller triangle and H is the height of the bigger triangle. So from this condition we can get the value of DE. So DE equals to H minus Y into B by H, because VC equals to V. You can see this from the diagram. So to find the dA, we have the dE. So dA equals to dE dE into dy. D is the length and dy is the width. So dA equals to x minus y, h minus y into b by h into dy. So this is the value of dA. Now we can easily find the value of dm. So the elementary mass of the strip, that is equals to dA into sigma, that is equals to h minus y into b by h into dy into 2m by bh. So going to the next page, di, that is the next step, equals to dm into y square, as we are integrating over y direction. So putting the value of dm from here, we can get 2m by bh into h minus y into b by h dy into y square. That is equals to 2m by h square into y square into h minus y dy. So now I equals to integral 0 to h, 0 to h, because we are integrating the strip from here to here. So we put the values of the limit 0 to h. 2m by h square into hy square minus y cube dy. That is equals to 2m by h square hy cube by 3, that is the integration of this, minus y to the power 4 by 4, that is the integration of the second part, and put the limit 0 to h. So after calculation we will get that I equals to m h square by 6. So this is the value of the moment of inertia of a triangular lamina if we rotate it in the axis which is situated on its base. Now the next is finding the moment of inertia of a square lamina about its diagonal. So we're given a square lamina and the axis of rotation is from its diagonal. So we have to find the moment of inertia. So if we look carefully that a square lamina is actually, you can divide it into two triangular lamina, right? So as we have discussed earlier that in a triangular lamina equals to mh square by 6 if we rotate it about its base, right? So we can think that in this part the mass is m by 2 and in this part is the mass is m by 2. So simply moment of inertia of the lamina B, C, D of this lamina B, C and D about the axis BD about this axis is equals to 1 by 6 into mass is m by 2 into h square. H is this height. This height is h, and we can easily find the h, and that is equals to h equals to L by root 2. We all know. So L by root 2 whole square, and that is equals to ml square by 24. So the total moment of inertia is equals to 2 into ml square by 24. That is equals to ml square by 12. And that is the value of the moment of inertia if we rotate a square lamina about its diagonal. So if we do the summary of this derivation, we have just done we have just used the value of the previous derivation, that is the triangular lamina, and we have split the square lamina into two parts, into two triangular lamina, and then just put the same theory. Well, now here comes the theorem. There are two theorems in moment of inertia. The first theorem is parallel axis theorem, and the second theorem is perpendicular axis theorem. So the first theorem, parallel axis theorem, that says that to find the moment of inertia about a given axis of rotation, means we will be given we will be given an axis of rotation, and first we have to find the imaginary axis b dash. So this axis is actually given to us. This is given, and we have to find the imaginary axis b dash, this axis b dash, which is parallel to a dash and passing through the center of the mass of the body. So we have to find a axis which is parallel to this axis which were given, and that axis which we let, that is passing through the center of the mass of the body. Now we evaluate the moment of inertia of the body if it were rotated about BB dash. Now we find the value of the moment of inertia if the mass is rotated about the axis BB dash, and let it be IC. Then the moment of inertia of the body about the given axis AA dash is given by I equals to IC. IC means the moment of inertia about BB dash plus MD square. M equals to mass of the body, D equals to the perpendicular distance from the two axes IP and IC. So basically, which is given here, suppose that we have a sphere. We know that uh, in case of solid sphere, the moment of inertia about its center is 2 by 5 m square. Now, if we are asked to find the moment of inertia about this axis, which is r distance apart from IC, simply let's say this is IP. IP equals to IC plus m, mass of the sphere into perpendicular distance, that is r square, that is equals to 2 by 5 mr square plus mr square, and that is equals to 7 by 5 mr square. This is what the parallel axis theorem says. Now, the next is perpendicular axis theorem. So this theorem says that the sum of the moment of inertia of a laminar object about two mutually perpendicular axes lying in the plane of lamina is equal to the moment of inertia about an axis normal to the plane of the lamina passing through the two perpendicular axes. So basically this theorem says that suppose that there are three axes mutually perpendicular, axis IY and axis Y, axis X and Z axis. So if you want to find the moment of inertia across the axis IZ, you just simply add the mutually perpendicular axis, that is Ix plus Iy, and the sum of Ix plus Iy will be the value of Iz. So let's see an example. We have discussed earlier that in case of a square lamina, in case of a small square lamina, the moment of inertia across its diagonal, let's say this diagonal is across x-axis, this diagonal is across y-axis. So Ix equals to Iy equals to ml square by 12. This we have discussed earlier. Now, if we are asked to find Iz, which is perpendicular to this lamina, just simply put this theorem. Iz equals to Ix plus Iy, that is equals to 2 into ml square by 12, that is equals to ml square by 6. So this is the value of the moment of inertia if we rotate this square lamina across the z-axis perpendicular to its center. And this is how this theorem says. And finally, this is the last question of the video. This question is a very important question and a repeating one in various examinations. So let's see what the question says. The question says a circular hole of radius r by 2 is cut from a circular disc of radius r. It says that there is a hole in the circular disc which is cut from the disc, and the disc lies in the xy plane and its center coincides with the origin. If the remaining mass of the disc is m, then find A. Determine the initial mass of the disk. Determine its moment of inertia about z-axis. So basically, which is given here, it is that uh, there was a disk of mass. We have to find the initial mass. There is a disk, and a small disk of radius r by 2 was cut from that disk. And we have to find that what was the initial mass of the disk, and we have also find the moment of inertia of this system about z-axis. So to find the initial mass, eh, let sigma be the surface mass density of the plate given by sigma equals to m by pi r square minus pi r by 2 whole square. So first we have find the surface mass density, and that is equals to m by pi r square minus pi of r by 2 whole square, because the area we can see the remaining area is the area of the bigger circle minus the area of the smaller circle. So that is equals to sigma equals to 4m by 3 pi r square. Now initial mass of the plate, let's say m1, equals to sigma into pi r square. So let's say the before the smaller radius disk was cut, the area of the plate was pi r square. So to find the initial mass, we have just multiplied the initial area with the surface mass density, and that is equals to 4m by 3 pi r square into pi r square. That is equals to 4 by 3 m. So this is the initial mass. And let's proceed further. B part. That is where asked to determine the moment of inertia about z-axis. So we have to find the moment of inertia about z-axis. So let's do it. The given arrangement may be considered as a combination of a circular plate of mass 4m by 3 and of negative mass m by 3. So in this case we have thought that this arrangement was split it into two parts. That is the initial mass, that is of m, initial mass of 4m by 3, negative mass of m by 3. Okay, so we have split this into two parts. Positive mass of 4m by 3, that is the initial mass, and the negative mass m by 3, that is the smaller disk which you have cut from the initial mass. So we will find the value of moment of inertia of these two individual and add them to. So now moment of inertia of the big disk. moment of inertia of the big disk equals to I equals to m mass, that is 4 by 3 m r square by 2, because we know that I equals to m r square by 2 in case of disk. So that is basically 4 m r square by 6. Now we will find the moment of inertia of the small disk. That is I2 equals to mass of the small disk into square of the radius of the small disk by 2 plus, and now here we will apply the parallel axis theorem. Let's see from the diagram. So this is the desired axis of theorem, and we know that moment of inertia from this axis, which is passing through the center of mass of the smaller disk, that is IC equals to m to r square, r2 square. R2 equals to the radius of the small disk. So we can say that IT, if we say that this axis, the desired axis IP, equals to IC plus m2 r, r by 2 whole square. Because the perpendicular distance from this two axis is r by 2. So we can say that I2 equals to IC, that is IC plus mass into mass of the smaller disk into perpendicular distance square, that is r by 2 whole square, which is equals to m r square by 24 plus m r square by, and that is 3 into 4, 12, equals to 24 is in the denominator and here 3 mr square, that is equals to I2. Now I equals to I1 minus I2, where I1 equals to the moment of inertia of the initial mass, and I2 is equals to moment of inertia of the smaller disk, which was cut out, r by 2, and that is equals to I1, that is 4 mr square by 6, 4 mr square by 6 plus minus I2, that is 3 mr square by 24, 3 mr square by 24, that is equals to 24, 16 minus 3 mr square, that is equals to 13 mr square by 24, and this is the final value of the moment of inertia of this disk about the axis perpendicular to its plane.